the very rare trajectory. This is 3i Atlas. This is Mars. 3i Atlas is about to swing by, and a fleet.
A few months ago, our solar system welcomed its first interstellar visitor in nearly 6 years, the third it had ever witnessed.
We've got some fresh images of 3i Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system.
The feeling of excitement was bubbling in both scientific and regular circles alike. And yet, almost as immediately as this flash of extraterrestrial light flickered in our eyes, it vanished again.
The supposed comet is catching the attention of some of the nation's most renowned scientists, as one Harvard professor is raising the theory this may actually be a piece of alien technology.
Today, we take a look at 3i Atlas, what it is, and what its sudden disappearance means for us, and how another member of our solar system might be the only link we have left to it.
That we have a literal interstellar comet, interstellar visitor in our midst, and it's flying past Mars as we speak.
So we can fully grasp what all of this means for us, it's important that we take a good look and understand what 3i Atlas even is. Its story begins on the 1st of July, 2025.
On the 1st of July, NASA detected a mysterious object speeding toward Earth, and some actual bona fide experts think it might not be your typical space rock or maybe any kind of rock or a natural phenomenon at all.
When the NASA-funded Atlas Survey Telescope, based in Rio Hurtado, Chile, reported sightings of a comet that had just sped into our solar system. If you're wondering, ATLAS is an acronym for Asteroid Terrestrial Impact Last Alert System. At first, they just noticed a little speck of light that was moving relative to background stars. Then they started to look more closely, and that's when they noticed that this object, this speck of light, was active. Around its nucleus, there was some coma, an indication that this object was in fact a comet, which had come close enough to the Sun for its ices to start vaporizing. At the time of its discovery, it had an apparent magnitude of 18, was 4.5 astronomical units away from the Sun, and another 3.50 astronomical units away from Earth. Now, according to NASA, this new interstellar comet had originated from interstellar space and had arrived in our solar system from the direction of the constellation Sagittarius. So, this wasn't something that was orbiting in elliptical paths around the Sun, bound by its gravitational pull. No, this thing had a hyperbolic trajectory outside the Sun entirely. On July 2, they named it C2025N1, or as it's become more popularly known, 3i Atlas. 3i there means that this is the third interstellar object ever confirmed to be passing through our cosmic neighborhood, after one, I Oumuamua, in 2017, and two, I Borisov, in 2019. Currently, this comet is orbiting some 420 miles away from us. At the same time, it's barreling towards the Sun really fast, too, at around 135,000 miles per hour. Now, when it was first discovered, astronomers had to go back to check with old records. They pored through archive observations made before the comet was even discovered, hoping to see if they would be able to perhaps spot it in old data. The archives of 3 different Atlas telescopes around the world were trawled through, as well as the Zwicky Transient Facility at the Palomar Observatory in California. Turns out, they had actually captured this comet before, with observations from the 7th of May to the 3rd of June 2025, actually. We'd seen this comet 55 days before we even knew what it was. No one just noticed it back then. Now that it was out in the open, everyone started keeping an eye out for it. In July 2025, astronomers announced that the Gemini North Telescope had taken a look at Comet 3i Atlas. By August, images of 3i Atlas taken by the Hubble Space Telescope were released. Later that same month, the Sphere mission and James Webb Space Telescope had also taken a look at 3i Atlas. But surrounding all the excitement about this new discovery, there were also oddities as well. Some of the things these August sightings found complicated things even further. They discovered that the comet's coma was dominated by carbon dioxide, so much so that its CO2 to water ratio is about 8:1, extraordinary figures for a comet. For most comets we've studied, water vapor dominates the coma once they approach the sun. CO2 would usually be present, but in far smaller quantities. Here, it was the exact opposite. Carbon dioxide was leading the activity, with water playing only a minor supporting role. That single fact already set 3I Atlas apart from almost every known comet in our solar system, but then there were even more peculiarities. The presence of trace gases like carbon monoxide, water vapor, and carbonyl sulfide were found, although their relative proportions were a bit different from what we'd expect. Instruments picked up around 285 pounds of CO2 being released every second, compared to just 14.6 pounds of water and 14 pounds of carbon monoxide. Even cyanide and atomic nickel vapor were present in the mix. Now, nickel isn't exactly a novelty when dealing with cometary comae. The intrigue here, however, was how much nickel there was, and that there wasn't any iron present. That wasn't just rare, it was unheard of. Infrared observations by the James Webb Telescope further complicated the picture, as certain parts of the comet's emission unexpectedly deviated from classical comet models. There were even some signals that seemed strange or unmatched by standard dust and gas models. Normally, scientists can explain a comet's infrared spectrum using well-established equations that describe how dust grains scatter and absorb light, and how various gases emit as they sublimate. But in the case of 3I Atlas, some signals simply didn't fit. They deviated in shape and intensity, producing spectral features that didn't correspond to any standard combination of dust or gas. In other words, parts of its chemical fingerprint looked off, almost as if we were observing material that followed a different set of rules. These strange, unmatched signals left researchers questioning whether 3I Atlas contained unknown compounds, or familiar ones arranged in unfamiliar ways, perhaps formed in environmental conditions that don't exist anywhere in our solar system. And yet, as weird as the chemical makeup and trajectory of this comet were, it was the measurements of this comet that seemed to be causing the most trouble. Hubble images put an upper limit on the diameter of the comet's nucleus at about 3.5 miles, but there was the possibility that it could be much, much smaller. A little over 1/4 of a mile, in fact. And yet, another source, the Vera Rubin Observatory, had images predating the official discovery, which, using its reflective light, suggested a nucleus radius of 3.5 miles. That would mean 3I Atlas had a 7-mile diameter, making it the largest interstellar object ever observed. The comet's age. Since nobody could pinpoint an exact measurement for it, the next question would be, how old was this thing? We already mentioned earlier that 3I Atlas wasn't following a parabolic or even elliptical orbit. Rather, it was tearing through space on a path so extreme, it was clear that this object wasn't born here. It hadn't passed near any planet that could have slingshotted it to such speeds. That meant it could only have originated from interstellar space. By tracing its inbound trajectory across the night sky, astronomers pinpointed its approach to a specific region, the constellation Sagittarius, near the Milky Way's galactic center. In other words, this thing came from the heart of the galaxy. And unlike the 2 interstellar visitors before it, 3I Atlas didn't arrive from the north, the so-called solar apex, in which the direction the sun is moving toward. Instead, it came from the southern celestial hemisphere, traveling opposite the solar apex. Scientists were astonished. For almost forever, we'd always assumed that most interstellar objects should come from the direction we're plowing into, like bugs hitting a windscreen. Objects from the south were supposed to be much harder to spot, if they even existed at all. So 3I Atlas was either an incredibly rare catch, or our assumptions about where these objects come from need to be rewritten. To understand its journey more deeply, researchers broke down its hyperbolic excess velocity, basically its motion relative to the Sun, into three components: U, V, and W, corresponding to radial, transverse, and vertical motions in the galactic coordinate system. They discovered that when 3I Atlas entered the solar system, it had been moving away from the galactic center at about 31 miles per second. Now, for context, when Oumuamua entered the solar system, it did so with a hyperbolic excess velocity of around 16.2 miles. At the same time, it was climbing upward through the galactic plane at around 11.5 miles per second, a vertical speed that's unusually high compared to nearby stars and other interstellar objects. This unusual tilt suggests it doesn't follow the same calm, flat orbital paths as most stars in our neighborhood. Instead, it likely belonged to the thick disk of the Milky Way, a population of ancient stars and bodies with lower heavy element content than the Sun. And that's where things get even more fascinating. In July 2025, a team led by Matthew Hopkins used this velocity data, combined with population models of the thick disk, to estimate the comet's age. Their results? With 68% confidence, they could place 3I Atlas as being somewhere between 7.6 and 14 billion years old. Our entire solar system is about 4.6 billion years old. So this comet could very well have been wandering the galaxy long before the Earth even existed. That would make it the oldest comet humanity has ever observed. A separate study by Astor Taylor and Darrell Seligman offered a slightly broader but still astonishing estimate: 3 to 11 billion years, which still placed 3I Atlas firmly in the category of ancient travelers. The disappearance. There were definitely a lot of oddities and novelties in what we were seeing, but at least we were seeing something. Telescopes across Chile, Hawaii, and orbiting platforms were locked onto it, collecting every possible photon. And the more we could see, the higher our chances of finally becoming sure of a few things. But then, suddenly, by late September, that window slammed shut. Now, this disappearance wasn't sudden like a light switch. It was gradual, a steady fading as the comet pushed deeper and deeper into the outer solar system. The more that happened, the more geometry turned against us. You see, Earth's telescopes don't just rely on brightness, but on angle. So if an object moves in such a way that it slips behind the Sun or sits at too small a solar elongation, tracking becomes nearly impossible without risking instrument damage. And that's exactly what has happened. 3I Atlas's peak magnitude was already too faint for the naked eye, and the more it receded, the more difficult it became for us to keep sight of it. Then, there was also the problem of its speed. 3I Atlas has always been moving on a hyperbolic trajectory at roughly 16 miles per second relative to the Sun, which is terribly faster than most solar system comets. Now, what that means is that the comet moves quickly enough for its position in the sky to shift subtly every night, forcing astronomers to constantly recalculate where to point their telescopes. Even the smallest of errors can lead to missed detections. And once the object fades below a certain threshold and the orbit grows uncertain, reacquiring it becomes exponentially harder. It wasn't that the comet had disappeared or slowed down. We were simply just looking straight toward the Sun, and the comet was too well hidden behind that blinding light. Think of it this way. It's like the difference between staring straight into a car's headlights versus watching the same car from the side of the road. Surprisingly, this isn't the first time Earth has lost track of something. Back in 2017, Oumuamua's brightness fell off so rapidly that large portions of its outbound journey were invisible to us. But with 3I Atlas, things are quite different. This is a much heavier object with a much more unusual chemistry, so losing track of it would carry bigger scientific consequences. But there really wasn't much else that could be done. The last confirmed observations came in early September across the southern hemisphere. But after that, coordinates slipped into an observational dead zone. When they tried to keep monitoring it using solar coronagraph instruments, that proved futile, as its contrast was just too low and faint. It simply wasn't bright enough to stand out against the background of space near the Sun. Even the Hubble Space Telescope couldn't help at this stage. Its solar avoidance angle is 50 degrees, and 3I Atlas drifted inside that limit. JWST's avoidance is even stricter, around 85 degrees. Ground-based telescopes were left staring into dawn skies, fighting atmospheric scattering, and still coming up empty. And while losing sight of it temporarily doesn't mean it's gone forever, it still poses a real risk. Predicting the future path of a faint, fast-moving interstellar object depends on extremely precise measurements taken over time. When those measurements stop, so does the refinement of the orbit. Even a small uncertainty early on can compound into thousands of miles of positional error after a few months. If Earth can't pick it up again later, it may leave the solar system without us ever seeing its final trajectory. That's why this disappearance matters. We have a unique interstellar object. As things stand, the largest ever found, chemically peculiar, potentially older than the solar system, and yet we're watching it slip beyond our instruments' reach. There's an eerie element to this moment. We're used to believing that human technology gives us omniscient vision. Satellites, telescopes, sky surveys. But the cosmos still has angles where our gaze fails. For the first time in its recorded journey, 3I Atlas has moved into a part of the sky where Earth is effectively blind. And yet, the story doesn't end here. The Mars angle. As it stands, 3I Atlas is gone, at least for now. But while Earth loses sight, there's another planet that doesn't. It's called Mars. But why does it have this vantage point? The answer lies in geometry. From Earth's perspective, 3I Atlas is slipping behind the Sun, effectively entering a no-observation zone. Telescopes on Earth and in Earth orbit are restricted. Pointing too close to the Sun risks blinding sensitive instruments, so the comet's path becomes a kind of observational dead zone. But then you look at the orbits of the planets in the solar system and realize that Mars is located on the opposite side of that geometry. So as the comet continues on its hyperbolic trajectory, Mars swings into a position where the angle between the Sun and the comet is wide enough to allow clean tracking. If Earth has lost sight, Mars is just stepping into the spotlight. This is more than a neat astronomical coincidence. Because Mars's orbital position puts it almost above the plane of the comet's incoming trajectory, spacecraft and telescopes stationed there, or even future orbiters, could observe 3I Atlas's behavior with minimal solar interference. In fact, Mars reconnaissance orbiters HiRISE and other instruments have already proven capable of detecting distant cosmic objects with extreme sensitivity. For example, in past years, HiRISE has captured passing asteroids and monitored impact events on Mars's surface from orbit with exquisite precision. Now, imagine training that same technology on a fast-moving interstellar object crossing the inner solar system at more than 129,000 miles per hour. Might sound impractical, but it is. We currently have 2 Mars spacecraft that we'll be able to observe 3I Atlas in the ultraviolet spectrum, namely the Emirates Mars Ultraviolet Spectrometer, EMUS, on the HOPE spacecraft, and the Imaging Ultraviolet Spectrograph, IUVS, on NASA's Mars Atmosphere and Volatile Evolution, MAVEN, spacecraft. And this isn't just some theoretical permutation. Simulations of 3I Atlas's orbit show that by late October and November, the solar elongation angle from Mars's point of view expands well beyond 50 degrees, which is comfortably outside the dangerous glare zone Earth-based telescopes, meanwhile, are stuck near zero elongation, effectively blind. And here's where things get really interesting. Mars could become the only place capable of detecting any sudden changes in 3I Atlas's structure, brightness, or trajectory. We already know that interstellar objects don't always behave predictably. Both 1I Oumuamua and 2I/Borisov surprised astronomers. Oumuamua, with its odd acceleration and shape, and Borisov, with its unexpectedly pristine composition. So if 3I Atlas undergoes outgassing, fragmentation, or non-gravitational acceleration while Earth is blind, Mars would be the first to know. This potential hasn't gone unnoticed by space agencies. According to recent ESA mission updates, teams have discussed piggybacking comet observations onto existing Mars spacecraft schedules during this window. NASA's MAVEN and ESA's Trace Gas Orbiter both carry instruments that, while not designed for deep space comet tracking, could theoretically collect useful data on the object's tail, dust emissions, or even subtle trajectory shifts. And if the object releases volatile compounds under Martian line of sight, Mars-based instruments could detect spectral signatures unavailable from Earth. Now, it's important that we bear in mind how unique this scenario is for modern astronomy. For the first time, another planet is better positioned than Earth to watch a newly discovered interstellar visitor as it speeds through the solar system. Historically, all interstellar objects have been observed almost entirely from Earth's perspective. This time, Mars might hold the observational upper hand. And there's a strategic layer too. Mars-based tracking could provide critical data on 3I Atlas's non-gravitational forces, helping scientists refine its outbound trajectory once it leaves the inner solar system. If the comet's behavior mirrors Oumuamua's mysterious acceleration, Mars may be the only vantage point capable of detecting that anomaly in real time. In a sense, Mars isn't just watching, it's acting as humanity's deep space outpost, catching what we can't see. What this means for us. Now, you're probably wondering what this has to do with us. And yes, while on the surface, losing sight of a faint interstellar comet might seem like a niche concern for astronomers, the implications of 3I Atlas reach far beyond telescope domes. We have to remind ourselves that this object isn't just another chunk of ice drifting through space. It's a rare interstellar messenger, and the way we observe it, or in this case, fail to, says a lot about where humanity stands in its ability to monitor the universe around it. We might very well not be as ready as we've always thought we are. Let's start with rarity. In the entire history of astronomy, humanity has only ever been able to confidently identify two interstellar objects before this. 1I Oumuamua in 2017 and 2I Borisov in 2019. 3I Atlas is the third, and yet every time we've found a new interstellar object, we've had to rewrite some of what we thought we already knew. When we found Oumuamua, it baffled scientists with its unusual acceleration and lack of a visible tail. Normally, when icy objects approach the sun, heat causes the ice in them to turn into gas, creating the visible coma or tail that we see. At least we thought should happen. And yet, Oumuamua despite passing closer to the Sun than Mercury, showed no visible outgassing in telescopes. No dust, no halo. That was shocking. Although it did bear similarities with textbook comets, Borisov shocked researchers even further with its chemical purity, suggesting it had come from a young, pristine system. Now, with 3I Atlas, we're offered the opportunity of a third data point, something astrophysicists have been craving for the longest of times. With only 2 objects, it was hard to generalize about interstellar visitors. But now that we've got 3, patterns start to emerge. Losing sight of it now means potentially missing crucial evidence about how objects form and travel between stars. And this is why we have to be so grateful for the observers that we have placed on Mars. And if Mars-based orbiters are actually able to successfully observe 3I Atlas during Earth's blind period, it would be the first time a multiplanetary observation network has been used to track an interstellar object. This is exactly the kind of infrastructure that would be essential for future planetary defense systems or for intercepting fast-moving deep space targets. And of course, all of that isn't science fiction anymore. We already have missions like the European Space Agency's Comet Interceptor, already designed to lie in wait for such objects. So if anything, 3I Atlas is only just testing how ready we actually are. Now, of course, there's always the fear of a possible collision. But from the figures we already have, we're in the clear when it comes to that. 3I Atlas is supposed to make its closest approach to Earth at around 1.8 astronomical units, or about 170 miles. So while 3I Atlas has definitely been that August visitor who didn't stay long enough for us to even put the T on, it clearly hasn't done us any harm either. It's just left us with a lot of intrigue. It is no doubt that this interstellar visitor has clearly made its mark even during the very short time it's spent with us. But what do you think about all of this? Is our inability to keep track of it from our planet a sign of our inadequacies when it comes to interstellar observation? Or is the fact that we've put observatory apparatus on Mars a testament to our resourcefulness and possible readiness in matters of outer space? Let us know your thoughts in the comments. And before you leave, check out this video about a shocking new development the James Webb Telescope just discovered.